Good day everyone. Today we are about to discuss the fundamental trigonometric identities. An identity is an equation that is true for every value of the variable in its domain. We list the fundamental trigonometric identities. So it is divided into four. The first one is we have reciprocal identities. In reciprocal identities, we have three. Cotangent x is equal to 1 all over tangent x. Secant x is equal to 1 all over cosine x. And cosecant x is equal to 1 all over sine x. Take note of these reciprocal identities. Next, we have the quotient identities. For quotient identities, we only have two. The first one is the tangent x, which is equal to sine x all over cosine x. And of course, you have the cotangent x, which is equivalent to cosine x all over sine x. Next, we have the Pythagorean identities. For Pythagorean identities, we also have three. The first one is sine squared x plus cosine squared x is equal to 1. Next, tangent squared x plus 1 is equal to secant squared x. Third, 1 plus cotangent squared x is equivalent to cosecant squared x. Remember those points. And of course, we have the negative angle identities. For negative angle identities, we have 6. For sine negative x, it is also equivalent to negative sine x. Cosine negative x, cosine x. Tangent negative x, negative tangent x. Cosecant negative x, negative cosecant x. Secant negative x, positive secant x. And cotangent negative x is equal to negative cotangent x. So in solving trigonometric problems, please do take note of the following: reciprocal identities, quotient identities, Pythagorean identities, and of course, negative angle identities. Now let us proceed with the following examples. Number 1, we need to find the values of secant x and sine negative x. Let's begin with letter A. Since tangent x is negative and cosine x is positive, then x lies in quadrant 4. For letter A, secant x is positive in the fourth quadrant. So we will use the Pythagorean identity to find secant x. Secant squared x is equal to tangent squared x plus 1. So this will be negative square root of 6 all over 2 squared plus 1. So we have here 6 all over 4 plus 1. 6 all over 4 plus 1 is 10 all over 4. Meaning to say, secant x is equal to positive and negative square root of 10 over 2. We choose the positive root, and so secant x is equal to the square root of 10 all over 2. Next, letter B. Sine negative x. From the quotient identities, we have tangent x is equal to sine x cosine x, right? Thus, sine x is equal to tangent x cosine x. Let me write. For quotient identities, we have here tangent x is equal to sine x all over cosine x. Meaning to say, sine x is equal to tangent x cosine x. Now let us compute. Since secant x is equal to the square root of 10 all over 2, then cosine x is equivalent to 1 all over secant x, right? And we have here 2 all over square root of 10. And we rationalize this one, we'll come up with 2 square root of 10 all over 10. Meaning to say, sine x is equal to the quantity of negative square root of 6 all over 2 times the quantity of 2 square root of 10 all over 10 equals negative 2 square root of 15 all over 10 is equal to negative square root of 15 all over 5. And we know that sine negative x is equivalent also to negative sine x. Therefore, sine negative x is equal to square root of 15 all over 5. In order for you to solve these problems, you need to be familiar and you need to be skilled in using the following fundamental trigonometric identities. So the following identities are very important in solving problems involving trigonometry. Okay? Before we proceed to our second example, take note that we also use fundamental identities to simplify trigonometric expressions and write a trigonometric expression in terms of other trigonometric functions. Let's proceed with number 2. Express in terms of sine and cosine only. So we have letter A, secant x plus cosecant x all over cosine x plus sine x. And for letter B, cotangent squared x minus tangent squared x. Let us compute first letter A. We use the reciprocal identities for letter A. So we have here secant x plus cosecant x all over cosine x plus sine x is equivalent to 1 all over cosine x plus 1 all over sine x all over cosine x plus sine x. Next, we need to take the LCD. So we have sine x plus cosine x all over cosine x sine x all over your cosine x plus sine x. Okay, let's simplify. Okay, we have here sine x plus cosine x all over cosine x sine x times cosine x plus sine x. Okay, let us now get the answer. We have sine x plus cosine x is 1 all over cosine x sine x. This is now our answer for letter A. So let me write secant x plus cosecant x all over cosine x plus sine x is equal to 1 all over cosine x sine x. Okay, next, letter B. Cotangent squared x minus tangent squared x. In letter B, we need to use the fundamental identities and simplify. So let me copy the given. Cotangent squared x minus tangent squared x. Use the fundamental identities. We have cosine squared x all over sine squared x minus sine squared x all over cosine squared x. We need to take the LCD. And we have cosine raised to 4x minus sine raised to 4x all over sine squared x cosine squared x. Okay, let us now simplify. Use your knowledge in algebra and of course the application of the fundamental identities. Okay, groupings. We have cosine squared x plus sine squared x. Then another group, cosine squared x minus sine squared x all over sine squared x cosine squared x. Okay. Next, we have here 1, right? Times your cosine squared x minus sine squared x all over your sine squared x cosine squared x. And for our final answer, let us now simplify. Equals. This will be cosine squared x minus sine squared x all over sine squared x cosine squared x. So let me write the given for us to compare. Okay, so we already expressed cotangent squared x minus tan squared x using sine and cosine only. This is for letter B. For letter A, we express secant x plus cosecant x all over cosine x plus sine x with sine and cosine only in the form of 1 all over cosine x sine x. Now let's proceed with example number 3. How about if we need to prove the identity? before I forgot, the fundamental identities can be used to verify if a trigonometric equation is an identity. Okay? We will illustrate, or I will teach you the different methods to prove an identity. Number 1, you need to transform one side of the equation into the other side using identities. Then you need to start working on the more complicated side. The goal side is left unmoved. Okay? Next, transform and simplify both sides of the equation and end up after a series of algebraic steps with the same form on both sides. 3. Multiply an appropriate expression to both the numerator and denominator of one side to come up after a series of algebraic steps with the other side. Take note that it can be useful to change all trigonometric function in terms of sines and cosines. And please remember that since the equation still needs to be verified as an identity, multiplying both sides by the same term cannot be done. Those are your rules in proving identities. Now let us examine the first one. We need to prove sine theta all over 1 minus cosine theta minus sine theta cosine theta all over 1 plus cosine theta. Is it equal to cosecant theta times 1 plus cosine squared theta? Just like what I've told you, the left side of the equation looks complicated, isn't it? And so we start with this side. And after that, we find the least common denominator, or your LCD, of the left-hand side and use fundamental identities. After that, we will simplify and come up with the right side of the equation. It is important to know your goal side so we can manipulate the appropriate terms. So let us focus on your left side of the equation. So let me write here equal sign. The right side will not be touched, so we will focus on the left. Sine theta all over 1 minus cosine theta minus sine theta cosine theta all over 1 plus cosine theta is also equivalent with sine theta 1 plus cosine theta minus your sine theta cosine theta times 1 minus cosine theta. That is our numerator all over 1 minus cosine theta times 1 plus cosine theta. Okay? In order for you to solve this one, again, I am reminding you to please memorize and be familiar with our fundamental trigonometric identities. And of course, you will need your algebraic skills in solving. Okay, so we have here sine theta plus sine theta cosine theta minus your sine theta cosine theta plus sine theta cosine squared theta all over 1 minus cosine squared theta. Okay, most of the solutions are already in shortcut. Okay, so I believe you master your algebraic skills in solving so that you will come up with this. Let's continue. Equals. Okay, let us simplify the numerator. We have there sine theta plus sine theta cosine squared theta all over sine squared theta. Okay. Next, sine theta plus sine cosine squared theta all over sine squared theta. Okay, we have there sine theta times the quantity of 1 plus cosine squared theta all over your sine squared theta. Next, we have 1 plus cosine squared theta all over your sine squared. The squared will be removed already. One plus cosine squared theta all over sine theta. Next, we have here 1 all over sine theta times the quantity of 1 plus cosine squared theta. And our final answer, they balance with each other. Cosecant theta times the quantity of 1 plus cosine squared theta. Okay. This is our answer. It balanced with the right side of the equation. Okay, here are our solution. For number 3, proving the identity. I repeat, you need to start with the left side and find the least common denominator and then use the fundamental identities. After that, you need to simplify and come up with the right hand side. Okay? So that is our example number 3. Next, for our next example, we will illustrate the method where both sides need to be transformed and manipulated so that the two sides will end up with the same expression. Number 4, verify that the equation is an identity cotangent squared x times cosine squared x is equal to cotangent squared x minus cosine squared x. The first step that we need to do is to change both sides in terms of sine and cosine. We will start from left hand side. We have cotangent squared x cosine squared x is equivalent to cosine squared x all over sine squared x times cosine squared x. Now we will use the Pythagorean identity. And we'll come up with cosine squared x times 1 minus sine squared x all over your sine squared x. From the right hand side, we have cotangent squared x minus cosine squared x. This is equivalent with cosine squared x all over sine squared x minus cosine squared x. This is your left side. Now, this is your right side. Okay, again, we need to transform each side so that we'll end up with the same expression later on. Going back with our right side, let us get the LCD. So we have here sine squared x. And to get the numerator, we have cosine squared x minus cosine squared x, sine squared x. Now let us compute. Cosine squared x times 1 minus your sine squared x all over sine squared x. Since both sides, look at our left side, and then your right side. Since both sides end up with the same expression, the given equation is an identity. Let us note. Cosine squared x times 1 minus sine squared x all over sine squared x is equal to cotangent squared x times 1 minus sine squared x is also equal to cotangent squared x cosine squared x. They are an identity. Okay, this is our solution for number 4. Again, both sides need to be transformed and manipulated so that the two sides will end up with the same expression. And since they are the same, then they are an identity. We next illustrate the method to prove an identity by multiplying the numerator and the denominator of one side by some expression which will simplify it and come up with the same form as the other side. So our next example will also make use of the second method. Let us now verify the identity tan x sine x all over tan x plus sine x equals tan x minus sine x all over tan x sine x. First step is we need to transform both sides of the equation in terms of sine and cosine. From the right side, we have tangent x minus sine x all over tan x sine x is equivalent with sine x all over cosine x minus sine x. And then your denominator will be sine x all over cosine x times your sine x. Okay, let us compute. We have in our denominator sine squared x all over cosine x. And for the numerator, we have here sine x minus sine x cosine x all over your cosine x. Okay. You analyze. So we have here sine x minus sine x cosine x all over cosine x times your cosine x all over sine squared x. Next, this will become sine x minus sine x cosine x all over sine squared x, followed by your sine x 1 minus cosine x all over sine squared x, and of course our final right side will become 1 minus cosine x all over sine x. Okay, this is our answer for the right side, which is our tangent x minus sine x all over tangent x sine x. So stand by. 1 minus cosine x all over sine x. Let us now compute the left-hand side. From the left hand, we have tangent x sine x all over tangent x plus sine x. This one. We will obtain sine x all over cosine x times sine x all over your sine x over cosine x plus sine x. Next, we have our denominator sine x plus sine x cosine x all over cosine x. And for the numerator, we have there sine squared x all over cosine x. Next, sine squared x all over cosine x times your cosine x all over sine x plus sine x cosine x. Okay? Next step, we have sine squared x all over your sine x plus sine x cosine x. After that, we'll have sine squared x all over sine x times 1 plus cosine x equals sine x all over 1 plus cosine x. Now here we will multiply our numerator and denominator by the quantity of 1 minus cosine x. So copy sine x all over 1 plus cosine x, and then we will multiply 1 minus cosine x for both numerator and denominator. Conjugate. We will conjugate this one. Okay, so we have sine x 1 minus cosine x all over sine squared x. Next, Pythagorean identity. So we have here sine x times 1 minus cosine x all over sine squared x. And the final answer will be, using the Pythagorean identity, we have 1 minus cosine x all over sine x. Let us compare the answer from the right side a while back. We have there 1 minus cosine x all over sine x, same with our answer for the left side, which is also 1 minus cosine x all over sine x. From both sides, we come up with the same last expression. The equation, therefore, is an identity. Take note also that not all trigonometric equations are identities. This implies that a trigonometric equation may be true for a particular value in its domain. These equations are called conditional equations. Let us consider this one. Determine if the equation is an identity or a conditional equation. We have sine x plus cosine x equals 1. If this is an identity, then it should be true for all values of x in the domain of the sine and cosine functions. Take note that the domain of both functions is the set of real numbers. So we substitute any real number, let's say pi all over 4 in the equation. Again, we will substitute this real number in our equation. So we have sine pi over 4 plus cosine pi all over 4. This is equal to square root of 2 over 2 plus the square root of 2 over 2. So we have the square root of 2, or this one is not equal to 1. Right? Note that the equation is conditional and is true only for, this will be true only for x is equal to pi over 2 plus your 2 and pi, or your x equals 2 and pi. Where n is any integer, so the given equation is not identity. So this is not an identity, therefore this is a conditional equation. I repeat, if one equation is an identity, then that should be true for all values of x in the domain. If the domain of both sides is the set of real numbers, and as we substituted pi over 4, which is a real number, we come up with this answer. Then we conclude that this is not an identity. Therefore, this is a conditional equation. That's all for our lesson in trigonometry. I hope you learned something. Goodbye.